नमस्कार, सुस्वागतम, अभिनंदन, केम छो, आदाबाज, सत श्री अकाल, राम राम, खंबागड़ी, वणकम, खुशामदीद, वेरी गुड आफ्टरनून। मैं अनिल भारद्वाज आप सभी का 84वें पीआरएल के अमृत व्याख्यान में स्वागत करता हूं, अभिनंदन करता हूं। I, Anil Bharadwaj, very warmly welcome you all for the 84th PRL का अमृत व्याख्यान. This व्याख्यान is also the 8th monthly व्याख्यान of the PRL का अमृत व्याख्यान 2.0, which is started on 30th of January 2013 after completing 75 episodes successfully every Wednesday starting from 4th of August 2021. PRL established in the year 1947, the year of our independence, by Dr. Vikram Sarabhai, the father of Indian space program. And we started the celebration along with the Azadi Ka Amrit Mahotsav to celebrate the Platinum Jubilee of PRL and to celebrate the legacy and to cherish the history of 75 years of PRL in the area of physics and space sciences. Today, that is Wednesday, 27th of September 2023, we have yet another very distinguished Vyakhyaan Karta with us today, Professor Venu Gopal Achanta, who is currently the director of CSIR National Physical Research Laboratory, in New Delhi, and who is also a professor at Tata Institute of Fundamental Research in Mumbai. Today, he is going to speak to us on the topic Metamaterials for light-matter interaction. And this Vyakhyaan is also coinciding with our SCOPE 2023 conference, which is going on in PRL. And so we have the SCOPE participants also attending this Vyakhyaan today. We greatly appreciate and thank Professor Venu Gopal for accepting our invitation and to be with us today for the 84th PRL Amrit Vyakhyaan. I would now request my colleague, Professor R.P. Singh, to kindly introduce our today's Vyakhyaan Karta to the audience at the WebEx, to the audience in the PRL's K.R. Ramanathan Auditorium, as well as all those who have joined us live on the PRL's YouTube channel. Over to you, Professor R.P. Singh. You have to unmute yourself.
Professor Achanta Venugopal. We know each other since long time. We have been meeting in many meetings and have been to NPL, where he is director since 2021. So, am I right? 2021, I think. Achanta?
Yes.
And before that, he was at TFR, professor in condensed matter physics. And he did MSc from University of Hyderabad, Central University. And after completing MSc, Masters in Science, he moved to TFR, did his PhD. And then in 2000, after completing his PhD from TFR, he went to Japan, Tokyo University. And doing postdoc, he was awarded another PhD from Electronics Engineering Department on semiconductor materials. And then he moved to TFR as faculty member, and he's still professor. And on deputation, again, whatever you say, he's director of NPL, National Physical Laboratory, CSR, Ahmedabad, Delhi. So it's really confusing, NPL and PRL. Many people confuse. So yeah, but NPL is in Delhi, PRL is in Ahmedabad. So, he has published more than 100 papers, very good papers indeed. And I think he's the only person who is working on single photon sources as well as single photon detector. So that's the beauty. He's working in variety of fields along with condensed matter. He has very good understanding in like good depth in photonics also. And with this word, I invite Professor Achanta Venugopal to give his colloquium. Over to you.
Thank you, RP. Thank you all the organizers for giving me this opportunity. Thank you, Professor Bharadwaj, for this opportunity. My apologies that I am not able to come in person, but hopefully I'll make it up sometime. As I mentioned, my last visit to PRL was for the student conference, and I really enjoyed that, and I really cherish as one of my best interaction with students, as well as one of the best conferences I attended. So that way, like it's my loss that I'm not there personally. Hopefully, I'll make it up next time. So today I'll be talking about metamaterials for light matter interaction, as mentioned. So I made it in a more tutorial like lecture so that I can take everybody along with the field, what is happening, and as an introduction to the field and the materials themselves and what we can do with it. Right. So in the introduction, I'll be talking. I made a long introduction and fewer results towards the second half of my talk. So I'll be talking about metamaterials, introduce them, then go to light matter interaction, what is all the fuss about, and then examples from our own studies on various studies involving metamaterials. Right. So just to begin with, we all begin in optics or any electromagnetic studies, like so we always start with the Maxwell's equations, the good old Maxwell's equations um, we, uh, tell us a lot about how electric and magnetic fields are related to each other. Then we start with medium with no free charges and no currents as an approximation. Then we go on to introduce the electric permittivity epsilon and the magnetic permeability mu. These are given by epsilon and mu, which are related to the displacement, electric displacement and the magnetic induction. Right. Now, once we have this epsilon and mu, they tell us how an incident electromagnetic radiation uh, reacts with to the applied field, or how the field or how the material responds to the incident electric and magnetic fields of the incident electromagnetic radiation. So the epsilon will tell us what's the response of material to the incident electric field, and the mu to the magnetic field of the incident radiation. Right. So once we have this epsilon and mu, these are mainly the bulk material properties which tell us the response, the electromagnetic response of the material. Right. These are in general, like, so we take non-magnetic materials, and so we take mu equal to 1 for simplicity, and we mostly consider epsilon because they are the stronger response compared to the mu, or the magnetic properties of materials. So if we take about insulators and dielectrics, insulators or dielectrics and metals, we have the simplistic models like the Lorentz model or the Drude model. In the Lorentz models for the dielectrics, we have the force damped oscillator model, where the applied electromagnetic field basically displaces the electron a bit from its mean position, and then the core of the atom will try to bring it back. So there is a restoration force acting on the electron. So this causes some the electron motion to have simple harmonic oscillation. So when we solve this force damped oscillator model, we get x as a function of time, or the electron position as a function of time. Right. From that, we get the polarizability or the polarization of the medium, which is in terms of the number of electrons and the electron charge and the mean position of the electron as a function of time. Right. So this is related to the P is related to the susceptibility chi. And so we can write by plugging this x of t inside this, we can write the susceptibility of the medium, which is given in terms of the electron density, electron charge, electron effective mass, etc. Right. So then we go on to define this epsilon as square of the refractive index, and which is related to the susceptibility as 1 plus chi. So for an oscillator, for a damped oscillator, so we have for the insulator, we have epsilon given in terms of the chi related, I mean, shown by this expression here. Right. So in case of metals, we have the Drude model where there is no restoration force because these are all free electrons. So x of t is, we obtain this expression, and then you plug it in the P, the polarization, and polarization or polarizability. And then here we have the interesting concept of plasma frequency. We all know about it. Then we go on to write the dispersion relation for epsilon. So that is epsilon is a function of omega, right? So this is once we know whether it's a insulator or a metal, so we know how to get the epsilon value. And similarly, we can also get mu response in the expressions for the mu for these, right? So the next one which we look at is the wave equation. So you just take the del cross on either side of and we simplify it and get the wave equation. Right here we get epsilon mu by c squared, and this is related to, so basically if we insert, so this expression, the wave equation has a solution which is a plane wave. The plane wave, if we plug E as a function of space coordinates and the time coordinate r and t, E as a function of r and t as given by a plane wave, where E0 is the amplitude and the direction of the electric field. So when we plug this in the wave equation, we get an expression given by this, where by simplification or writing k square in terms of omega square, like so we get the wave or the dispersion of the dispersion relation for the plane wave propagating inside this medium, where epsilon and mu are the dielectric permittivity and the magnetic electric permittivity and magnetic permeability of the medium in which the plane wave is propagating. And from this, we also get the k and lambda relation. So lambda is basically 2 pi over k. K is the wave vector. Right? So the velocity of electromagnetic wave is given by v is c by n, where n is square root of epsilon times mu. So n is the index of refraction, as we all know. Now, from the Maxwell's equations, we also know that E, H, and K, the electric field, magnetic field, and the propagation vector, they form a triad. And in case of positive index materials, or when refractive index is positive, is greater than 0, these, let's call these ordinary materials, which are materials which exist, which we normally see in nature. So for this case, the E, H, and K form a right-handed triad, and that's what is shown here. For these materials, the K, and the S, the pointing vector, the wave vector and the pointing vector are in the same direction. So this all we know from basic textbook concepts. However, in 1968, Russian physicist Vesalago, he published a 6-page article and considered what happens if epsilon and mu are negative. Right? They are not positive as in the case of ordinary materials, but we have epsilon and mu less than 0. So when we talk about n is equal to square root epsilon and mu can be positive or negative. Right? But because of the square root, so n can be plus or minus value of this magnitude, whichever we get from the square root term. So n can be either positive or negative from this expression. And most of the ordinary materials, or because in real life, we only see these ordinary materials which have n positive. So far, people have not considered n negative values. So he has done a small theoretical paper in which he considered what are the consequences of having epsilon and mu negative. So first thing he showed is that when epsilon and mu are positive, we have the right-handed triad, the wave vector and the pointing vector, the energy propagation are both in the same direction. However, if epsilon is less than 0 and mu is less than 0, and n is less than 0, the refractive index is negative, then in this case, E, H, and K form a left-handed triad. And in this case, the wave vector and the energy, they propagate in opposite directions. And he went on to show multiple examples, including inverse Doppler effect, right? Then how the Cherenkov radiation changes. And from the optics perspective, what is interesting is that when you have an incident beam and a reflected beam, right? So the reflection is happening at the interface of a ordinary material on the top, and the second one could be either ordinary material or, let's say, extraordinary material. Right? Extraordinary material is one which has epsilon and mu negative, and by virtue of it, and the refractive index is negative. So he showed that the reflected wave has no change. your incident angle is phi, your reflected angle is phi, right, remains the same. However, the refracted beam is towards the normal in case of ordinary material, but the refracted beam in the case of an extraordinary material, negative index material, is away from the interface. So the angle is minus phi instead of being phi in case of negative index medium. A consequence of this is if a lens is made of a negative index material, instead of focusing, the beam gets the collimated beam falling on it will get diverged. And a concave lens, on the other hand, which is made of n less than 0 material, it works as a focusing lens. So he went on to show that we can now have a flat lens. Like lens need not be, if we make lenses which are made of a negative index medium, an extraordinary medium, sandwiched between two ordinary materials, then we can have a perfect flat lens, right? So we need not have curvatures and all that to generate the phase differences and all that. So here, if you have a source in the medium one, which is, let's say, pointing a, a point source or an object which is emitting light, is emitting from that, and it's going diverging from the point source. And what happens is at the interface, right, there is a change from n equal to positive to n equal to negative. So by virtue of it, your e power ikx, like so, you'll have no longer a diverging beam inside the negative index medium. It becomes a converging uh, wave. And so, like all those components, high k vectors, which are actually evanescent in the positive index medium, will become non-evanescent or propagating waves inside this. So all the uh, high k vector components, high k components in the incident beam, so they all get lost because they're evanescent if they propagate as a positive index medium. But however, because of the shift from positive to negative index medium, the high k vectors are now propagating inside this, and then they get focused inside the medium. And then after that, they again start diverging. And again, at the other second interface, where from negative medium to positive medium, so they'll again start converging because the sign of n is changing. So n is related because k is equal to 2 pi over lambda. Lambda inside a medium is lambda by n, the refractive index. So depending on the sign, so your e power kx term, so will be changing in the plane wave. Right? So he showed that basically we can get perfect image because the high k vectors, which are basically evanescent, are no longer lost when you have a negative index medium confined between two positive index mediums, and it acts like a lens, as a perfect lens with no loss in the image or loss in the components information from the source to the image, object to the image. Okay. So now we seen that it's basically epsilon and mu, which are uh, which rule the response of the medium to the incident electromagnetic radiation. Now, as I mentioned, so epsilon and mu can be either positive or negative. So depending on that, when we plot mu versus epsilon, so you can have in the second quadrant, epsilon is negative and mu is positive. So all the metals and plasmas, they all form under this category. The electric field is evanescent wave, like because the field doesn't penetrate into the metal or the plasma. So most of them are reflecting, and we know that. Like so, and the first quadrant is the most obvious one, where we have positive index materials. Most of the insulators or dielectrics are in this case. We have the right-hander triad, and there is a forward propagating wave, and n is basically square root of epsilon times mu. And n is real in this case. Okay. So in the metals, like n is imaginary, so you have n plus ik, so there is always loss component involved. In the fourth quadrant, we have epsilon is positive, but mu is negative. There are some ferrites where they have these specific resonances where the mu is negative for these materials. But the most interesting thing is in the third quadrant, where both epsilon and mu are negative. As I mentioned, the consequence of this is that n is equal to n is negative, n is equal to minus of square root epsilon mu. And here also like n is real. And here EHK form left-handed materials, and energy propagates in the opposite direction to the k vector, wave vector. So these are called the negative index materials or metamaterials to begin with. However, like so things are changing now. So uh, how do we generate these? So there are several ways. So one is to use these effective media. So we all know about the diffraction limit. If the size of our particle or a size of a medium is much smaller than the wavelength of light, then the wave most of the time passes through with little scattering or distortion, so distortion of the wavefront. So we'll not be able to resolve the presence of any obstacle in its path. So we cannot see an atom in a optical microscope. However, we can have an effective medium whose dimension is of the order of wavelength or bigger, but it is made of multiple constituents. It can be more than one constituent whose individual dimensions are much smaller than the wavelength of light. So for example, so we can have two materials of epsilon 1 and epsilon 2 dielectric constant. Mu, we can take them as 1. So these are non-magnetic materials for simplicity, or we can consider mu as well, mu and mu2. And let's say thin film of diamonds like d2 are much smaller than the wavelength of light. Then we can say that the effective epsilon for this case is epsilon 1 d1 plus epsilon 2 d2 by d1 plus d2, or and similarly mu effective can also be written. So in this case, we can distinguish for incident electromagnetic radiation, the electric field is parallel to the layers or perpendicular to the layers. If it is parallel to the layers, if E is parallel to the layers, we again look whenever we do the electromagnetic problems like boundary value problems, we always look at continuity of the electric field and continuity of the um, first derivative of the field. So from that, like so we get the tangential component of the field at each interface is continuous, and also the induction vector, the D parallel, which is equal to epsilon parallel E parallel, will become an weighted average in each of these layers. So that means like so E1 equal to E2 is equal to E parallel, and F1 epsilon 1 E1 plus F2 epsilon 2 E2 is equal to epsilon parallel E parallel. Now if we have E perpendicular to the layers, then what we have is the normal to the surface component of D is continuous across the interface. And E for the effective medium is to be approximated by the weighted average, which are given here. So from these, what we can get is for a layered structure like this, a simple layered structure, which is an effective medium, we can now generate materials which have different type of response in different directions. Right? So the E parallel and E perpendicular expressions are given here. Depending on what the epsilon 1 and epsilon 2 are, now we can design materials which can act, for example, epsilon 1 is negative, that is a metal, and epsilon 2 may be positive, like a dielectric. By combining these two, we can make materials which act inhomogeneous in the sense that with respect to the propagation of light, in the perpendicular plane, it could be acting like a metal, and in the other direction, it may be acting like an insulator, or vice versa. It is metal here and then dielectric or insulating in plane. So we can design such kind of materials now by combining metals and dielectrics. Right? So one we have seen is negative index media, where epsilon and mu are negative, and n by virtue is negative. So these are purely the so-called extraordinary materials with which the field sort of started. Then we are talking about effective media, where by combining metals and dielectrics, we can generate effective media with unique epsilon and mu values. So we can have anisotropic media now by combining these different materials. Right. Now, once we have metals, there is another concept which we need to invoke, which are the plasmons. Right. So in the plasmons, so if you take a metal nanoparticle and put it in a dielectric medium, so the free electrons in the metal nanoparticle, they can oscillate at certain natural frequency. Now, if we have an external field which is incident at a frequency which matches with this resonant frequency of this free electron oscillation on the metal surface, so we can have a resonant transfer of energy. So depending on that, your scattering spectra will show different colors. So during the positive half cycle of the applied electric field, the electrons are pushed down, and during the negative half cycle, you can see that these electrons are pushed up towards the top of the metal nanoparticle. We obviously know that these are not, the electrons are not moving away, they are still confined to the metal nanoparticle, but just oscillate about the mean position. Right? So the advantage or the consequence of exciting these particle plasmons or the plasmons, the collective oscillation of these electrons on the surface of the metal nanoparticle, is that we see a strong localization of the field. Right? Now, we have diffraction limit, which says that the scattering object should be of the dimension of lambda by 2 or bigger. But now, because of these plasmon resonances, we are coupling electromagnetic radiation to these localized plasmon resonances, where the field, the electromagnetic field from light to the plasmon mode is converted, and then it's going to be confined to dimensions much smaller than the wavelength of light. So we are beating the diffraction limit and taking light to subdiffraction dimensions. So we can also have this so-called surface plasmon polaritons, where you have a interface of a epsilon positive material and epsilon negative material. So we solve the Maxwell's equations with the boundary value problem that, I mean, the usual thing which we use for a Snell's law, right? In the Snell's law derivation, like we look at how much is the reflected and how much is the refracted beam or transmitted beam. But in this case, we ask a question like, is it possible to have a solution to the problem where there is a wave which is propagating along the interface direction? So it turns out that the solution shows that it is possible, provided you have metal and insulator interface, that is epsilon negative and epsilon positive materials forming the interface, and you have less number of electrons at one place, more number of electrons at another place. So you have a charge density wave which is propagating along this interface. This is a surface wave by definition, which means that away from the interface, you have a evanescently decaying uh, field away from the interface. So you're actually confining the field to dimensions, again, much smaller than the wavelength of light. Right? And the dispersion relation is given by this Kxx or Kspp, the surface plasmon polariton momentum, is given in terms of omega by c times square root of epsilon 1, epsilon 2 by epsilon 1 plus epsilon 2. Epsilon 1 and epsilon 2 are the dielectric constants of a metal and the dielectric, which form the interface. Okay. So when we plot the dispersion for the light line, this is for the photon, dispersion for the photon, and this is the dispersion for the plasmons. We see that for a given photon frequency, we cannot directly shine light this charge density wave or the surface plasmon polariton wave, because there is a momentum mismatch. Right? For any resonant transfer, we need energy momentum conservation. So for the same energy photons and plasmons, there is a momentum not shine and exit these one modes. These SPPs are TM polarized. And angle. So your diffracted lambda is defined and for a given order. When you change the theta, your lambda is changing. So that's what is plotted here for a simple grating structure. So this is the wavelength versus incident angle. Incident angle can be converted to K. K is nothing but, K0 sine theta. Theta is the angle of incidence, and wavelength can be converted to omega. So this is the dispersion relation, omega versus K. You can convert it. The interesting thing is that for the same mode, diffraction mode, is the one order of the grating order, right, which is changing with the incident angle. But the interesting point is the line width of this. So the line width is changing, increasing as the mode is going up. As you are um, increasing the angle, the wavelength is shifting, obviously from the grating expression. However, it's the line width is changing, which means its lifetime is also different. So the plasmon mode is slightly different property depending on at what angle we are launching it. Right? So then the third one concept is metasurfaces. Right? The first one is effective media. The second one I'm talking about is plasmons. When we can excite plasmon resonances to beat the diffraction limit and make materials which are unique in nature compared to naturally existing materials. And the third one is, instead of making two-dimensional or three-dimensional complex structures, we can just pattern the surfaces. This has evolved over the last um, decade or so, or less. So there are three main types of mechanisms where metasurfaces are used to manipulate the phase variation for a given polarization. So for example, you can take linearly polarized, circularly polarized, or completely polarization independent structures. Right. So each one is defined in terms of, for example, for linearly polarized case, or we can look at generalized Snell's law. So where, for example, if you have a circularly polarized light coming at an angle, right? So you have instead of having circular shape, like so, where at the point of incidence, so you'll see that it gets elongated slightly, right? So you'll have certain phase difference from one end to the other end. Right? So if one it's phi and the other phase at the other end is phi plus d phi, and the spread of the spot is dx, what we can talk about is ddx of phi, so which is the change in the phase across the beam position, right? From Snell's law, now it becomes a generalized Snell's law comes out that if you have a um, surface which is patterned or having antennas or complex structure, right? So you can have a spot coming in because of the ellipticity. You'll always see a difference in the phase from the two edges, and that can be manipulated by structuring your surface. Right? So if we take that additional phase difference across the beam into consideration, the Snell's law is generalized to have this sine theta t and t. This is in the refraction or the transmission direction, minus the incident one sine theta 1 times ni. This is the refractive index of incident and the transmitted media, and lambda 0 is the in the vacuum wavelength, lambda 0 by 2 pi times the phase change. So this is the additional factor which comes in if you want to consider a metasurface or patterned surface in right. So people have showed these kind of structures. If you have a metal rod, you can excite a dipole resonance or higher order multipole resonances. If your electric field is oriented along this direction, you can have a plus and minus. So a dipole can be excited, or you can have quadrupole and higher order modes. Right. So you have a resonant. This is a dipolar resonance, and there is also phase associated with it. But if you take two of these rods and align them at an angle, right, now each one can have a mode, a dipole or higher order mode, and these two modes can couple to each other, and this leads to a certain interaction of the coupled modes and the phase with the phase specific phase relation between them, depending on how these two modes interact with each other and what is the geometrical orientation of these two, right? So if you're exciting either in the S direction with the electric field along S direction, then we'll be exciting the symmetric modes. And if the electric field is along this A direction, we can excite these antisymmetric modes, right? These two can, so basically you can have, because of these coupled modes, you can have symmetric and antisymmetric modes like in a standard coupled mode theory, right? So the currents can be also propagating in different directions, which are shown by these arrows. This is for symmetric modes, and these currents are for the antisymmetric modes. Right. Now, the interesting thing which was shown in 2011 was you can align these scattering elements. Let's call these antennas, as per the parlance in the um, field, right? So you arrange these antennas in different fashion. So now this is your unit cell, which has this set of 8 scattering elements or antenna which are aligned. Now you can have a periodic arrangement of these. Now, if these are put on top of a surface and we shine light from bottom, so each of them is going to scatter the beam in slightly different way. Now, these antennas, each one of them is so designed such that the phase change from one to the other is about pi by 4. So from one end to the other end, we are changing the phase of the field, incident field by, or the scatter field by 2 pi. Right. So you can get a phase front which is aligned at a designed orientation, right? So that's what is shown by this red line here. So now what we're doing is we're actually manipulating the phase of the scattered light by arranging our surface, the surface of our substrate. So these patterned surfaces, which can be used to control the wavefronts or the phase of these incident beams, electromagnetic radiation, these are known as the metasurfaces. So you can also have these orbital angular momentum states by combining different orientations of these antenna structures, or you can have just linear elements which are arranged in a specific way so that you can get different response for the light, right or left circularly polarized lights. Right? So these metasurfaces are popular nowadays to because you don't need complex dimensions. Extra dimensions are not needed. Just by modulating the surface, we can get these. Right. The second part, which I want to talk about, is the light matter interaction. So in this, so we always look at a cavity, and we look at an atom inside the cavity. So the field, the quantum optics, what we look at is how the cavity photons and the two-level system, the atom, interact with each other. So if you have a single atom inside a high Q cavity, just two mirrors, a Fabry-Perot cavity. So depending on the decay constants or decay rates of the atom, and that's gamma, or the cavity photon, which is kappa. So we can have a coupling between them, the photon and the atom, and the coupling constant is given by G. So in this, from 1960s, from the invention of laser, people studied this extensively, the light matter interaction inside a cavity. And we generally look at weak coupling regime and the so-called strong coupling regime. In the weak coupling regime, we talk about Purcell enhancement, Purcell effect, where we talk about how the lifetime of the atom gets modulated because of the coupling to the cavity. Right? And compared to atom or a two-level system inside vacuum, when you put it inside the cavity, its emission gets modulated. The change in the emission properties with respect to the vacuum are basically the Purcell effect. Right? Or we can have strong coupling regime, where the G is comparable to gamma and K and kappa. So here we see that there is splitting of the energy levels in the frequency domain, or you see these oscillations in the time domain, which are known as the Rabi oscillations. So this is the strong coupling regime. However, people are now looking at domains which are much stronger, much different interaction strength, much different from that of the weak and strong coupling regimes. So these are the non-perturbative regimes, where you have, instead of having one single atom, you have, for example, an ensemble of atoms where there are n number of atoms inside a cavity. So to go from weak to strong coupling regime, we have to have very high Q factor cavities. But then the Q factors of the cavities have certain limitations to achieve. So other way to go is by increasing the number of atoms or number of two-level systems inside the cavity. So once you have this ensemble of these two-level systems, we now have cooperativity effects where we're no longer talk about single atom, but then these act like a collective ensemble of atoms. Right? And here the coupling constant is no longer G, but it is G times square root n. Right? So obviously, depending on the number of atoms which are inside, so we can have very large coupling constant. And now we are talking about going to this so-called ultra-strong coupling and deep strong coupling, where even the ground state is supposed to get modulated as per the theoretical calculations which have been presented. Right. So just to show the Rabi model for interacting two-level systems, so we have uncoupled Hamiltonian given by this, and the quantum Rabi model is given by the second expression here, where the third term is the coupling constant. Typically, in the weak and strong coupling regimes, people ignore these A dagger sigma plus and A sigma minus in the rotating wave approximation, and this is known as the Jaynes-Cummings Hamiltonian, which is given by this. Right. However, we need to, if we want to go into non-perturbative regimes or ultra-strong and deep-strong coupling, we need to solve the complete Rabi model. Right. So to study these different coupling regimes, what we need is, just to show this, like, so only there are 2 reports so far in the ultra-strong coupling regime, and handful of reports in the, sorry, this is in the deep-strong coupling, and the handful in the ultra-strong coupling regime where the G is between 0.1 and 1. So above 1, there are just 2 reports, right? And all of them are at low temperatures and specific conditions, extreme conditions. Right? So to do these light matter interaction studies, so we need two-level systems. So these can be quantum dots, which are the solid-state equivalents, or defects in nanodiamonds or 2D materials. We can also use metamaterials for mimicking two-level systems. For example, this kind of structure shows Fano resonances, and electromagnetically induced transparency can be mimicked here. Or in stretchable metamaterials, we showed that we can go from EIT, electromagnetically induced transparency, to all the way up to autotone splitting, where the energy levels are split into orthogonal modes. Right. So and the cavities can be anything from simple Fabry-Perot cavity of 2 planar mirrors to whispering gallery modes, or photonic structures. These are photonic crystals. This is distributed Bragg reflectors. And this is plasmonic structures, 2 plasmonic antennas. Between them, you can enhance your field. And if you can put one single atom inside that, like, you'll have strong interaction between them. And people are now looking at all dielectric metamaterials because metals are lossy. So now we are talking about resonances like bound states in continuum. Right. So I mentioned about these anisotropic materials. I'll show one consequence of this. This is a hyperbolic metamaterial. Right. So here, as I mentioned, so you can have it. It's no longer a isotropic spherical dispersion profile, but you can have epsilon xx and epsilon zz to be different. So they can be negative or positive. So depending on that, you can have different dispersion profiles where very high K vectors are also possible modes within this material. Right. So from the effective medium theory, so we can get for a alternating layers of dielectric, zinc sulfide in this case, and gold and the other metal. So you can have a stack of these, and we can get epsilon perpendicular and epsilon parallel. And by choosing the ratios properly, dimensions properly, we can get, for example, epsilon xx is goes to negative, so below, say, 500 nanometer, and epsilon zz is positive. Right? So zz direction is insulating or dielectric, and epsilon xx is metallic in response. So once we have that kind of material, so we have put a single nanoparticle. This is a nanodiamond inside this material, and looked at emission from this. So because the high K vectors are possible modes within this hyperbolic metamaterial, so it will collect most of the light. The collection efficiency increases. However, when it comes out of the hyperbolic metamaterial, it's again a evanescent mode. So it's going to get lost. So what we do is we did a antenna on top. The antenna is designed such that depending on in a confocal microscope, so we have a home built confocal microscope, so we know what is the numerical aperture of the lens and all that. So based on that, we designed this antenna so that we collect most of the light emitted from this particular structure. So we designed it for emission at say 15 degrees and collected photons coming out of them, and then tested for if you have a nanodiamond with a single NV, so the possibility of having single quantum dot emission from these structures enhances. So we showed that single photon emission. So, but however, one problem is whether it's a quantum dot or a nanodiamond. So depending on the material which we use, so it's there is a degradation which happens because um, there's a diffusion of these chemical compounds inside this quantum dot, and which reduces the size of the quantum dots and its emission shift to blue uh, wavelengths, so shorter wavelengths. So to avoid that, like, so we studied numerous materials, both insulators and metals, to find out which give less scattering and more stability to the quantum dots or nanodiamonds, and eventually found that hafnium dioxide reduces the blinking effect. So blinking is because of for these nanoparticles. So the surface is a defect. So any electron which reaches the surface state stays there for a long time, and because of which, like, so the emission gets suppressed for a certain time till the electron goes back into the into the nanoparticle. So we showed that we can actually improve on the blinking, so the times reduced, and we showed single photon emission from these structures. We have proposed a simple structure where if you put two quantum dots inside a dielectric and bring it very close to the metal surface and excite one of these quantum dots. Right. This quantum dot emission is possible to excite the plasmon mode at the metal air interface. Air is in between these two, the dielectric epsilon d and epsilon 1. The epsilon 2 can be air or any other dielectric. If you consider air, just simply at the metal air interface, the plasmon mode is excited. This propagating plasmon mode excites the second quantum dot and makes these two quantum dots coupled together, because of which we showed that the emission together coming out of this structure is a noon state. That is, both the photon emitted by uh, particle 1 and photon emitted by particle 2, both either go in detector 1 direction or in detector 2 direction, and never like one here and one there. Right? This is the so-called noon state in quantum optics. So we also working on metasurfaces for atom chip. So this was work initiated about 6-7 years ago with Professor Hema Ramchandran when she's unfortunately no longer with us. But so this is a simple grating structures. The gratings were designed in such a way that the idea is we launch light, and each of these grating reflects one beam each, and then these are from the surface of the substrate about 3 to 5 away, so we can make them co-focus together and use it for atom trap applications. Right, we had certain issues with it. These structures were tested at DRDO, and we found some issues with it, and moved to other dimensions, other geometries, which I'll show a little later. But this was with Professor Umakant Rapol, where we showed that if you take a disk of metal disk, either gold or silver, we showed that gold is better. So the top of the disk, it acts like a trap potential. So we calculated that. Then we did near field measurements to show that we do have this trap-like potential, and it's suitable for trapping atoms on top of these disks. Okay. So the measurements were never done, the actual trap measurements, but I've seen in literature later on that polystyrene beads have been trapped on top of such structures. Right. So this is the metasurface where we took these silicon rods, and we showed actually the one which I mentioned about the gratings here. The problem is the silicon which is here, unpatterned silicon, that was also reflecting some part of the um, incident light, and that was spurious thing which we wanted to stop. So we made this kind of structure. These are silicon rods, and the dimensions are chosen to get the phase differences properly so that we can reflect certain polarization components and how much intensity and at what position they get reflected from. So here it's basically above 5 mm from the surface, we can get 4 beams coming from 4 different directions, and then they can form these trap beams. Right? So this has been experimentally made, and we are looking at optical trap experiments currently. So I'll show one example of a perfect absorber. So for different applications, sometimes we need 100% of the light to be absorbed within your, say, few nanometer thick um, active or absorbing material, lossy material. So for example, it can be 10 nanometer silicon, or 3-4 nanometer silicon, or germanium, or some other material, right, with a small absorption coefficient. So one of the ways, one of the first things to do is we need to reduce the loss because of the reflection. So which means we need to couple entire incident light to this active medium, or we get impedance matching. So for that, so what we need to do is basically the reflection has to be suppressed, for that the impedance of the top layer, for example, sorry. Yeah, okay. I'll go through the flow. I'm just looking at the clock, and I thought I'll have 5 minutes more. So, okay. So if we have impedance matching layer, then we have the active layer, and then we have the top and the bottom thick metal layer, which suppresses all the transmission. So once we suppress all the transmission, and we are already suppressing the reflection because of the impedance matching the top layer. So then all the light will be absorbed within the small or thin absorbing layer, which is in between these two metal layers. Once we have such a 3-layer structure, metal, dielectric, and metal, we can have Fabry-Perot resonances. And as I mentioned, we can have a plasmon mode here, we can have a plasmon mode here. Depending on the thickness, they can couple to each other, and we can have symmetric, anti-symmetric modes. So the symmetric mode has profile like this, and the anti-symmetric mode has SPP mode. Like the charge distributions are given here just for comparison. So this has been shown in a dielectric metal dielectric kind of structure, where because of the coupling we see states which are anti-crossings. So instead of just crossing over non-interacting plasmon modes, we can have modes which will interact with each other. So instead of crossing over, we do see these anti-crossings or gaps which are generated in the dispersion plot. Right. Now coming back to the perfect absorber, so we have the impedance matching layer, we have the middle absorbing layer, and the bottom thick metal layer to block the light transmission. Now the top metal layer can be patterned, like shown here, 2D patterns or 1D grating-like structures, or they can be planar structures. I'll show one example where pattern can be, you can make it broadband by choosing different shapes, scattering element having different shape for different wavelength regions. So squares for this region, circles in this region, or crosses or diamonds for this region, and arrange them in a square lattice with randomly distributed shapes. Right. So then when we look at the reflection, we showed that we can get up to 99.86% suppression of reflection and absorption, and there's zero transmission, and suppression of reflection leads to 99.86% absorption in a thin 10 nanometer thin silicon layer. So we showed a layered structure with a silicon dioxide layer on the top. With here we have shown that because it's a SiO2 which is index matched to a glass cuvette, so we can put a flow cell on the top and flow the analyte, and we can do these ellipsometric measurements to get close to single photon level sensitivity in detection of biomolecules. So here I'm showing data up to 100 femtomolar sensitivity. Right? So we also developed this quasi-periodic structure. If you have arrangement of scattering elements in a square lattice, the Fourier transform is a square lattice, and this is a discrete structure. However, the same number of scattering elements are arranged in a 5-fold rotation symmetry. You see a very dense K-space, which allows you to have polarization independence. Then you have broadband response, from these structures. There is no incident angle dependence also. We showed that, and we excited these gold air interface plasmons and gold quartz interface plasmons, and they couple to with each other, and we can get up to 20% absolute transmission from 100 nanometer thin gold films. Without patterning, 100 nanometer thin gold film transmits only 0.1% absolute light. However, once we pattern with this quasi-periodic structure, we can get up to 200 times or 20% absolute transmission through these structures. We showed second harmonic generation, broadband second harmonic generation from these. And we looked at density-dependent quantum dot photoluminescence from these structures. We showed basically that there are these oscillations which are happening at short time scales, but then these timescales are much longer than the plasmon lifetime. So when the plasmons are no longer expected, still we see these oscillations, and these are density dependent. Only at very high densities we see these. At low densities or non-resonant excitation, we do not see these oscillations. And we measured the Goose engine shift, the plasmon propagation length, and measured the emission coming out up to these propagation length of the plasmons. So the idea here is that we have quantum dot clusters which are on top of this plasmonic structure. This is the right part is the unpatterned metal region, and this part is the patterned metal region. So the quantum dot clusters are excited with a excitation spot, and these emission from these quantum dots excite plasmons which propagate and excite these clusters which are on unpatterned metal region. These two are slightly shifted in resonance due to lamp shift, and the oscillation, the resonant coupling between these at high densities. So you see these oscillations in the time domain, the Rabi oscillations in the time domain with plasmon uh, much longer than the plasmon lifetime, because these are exciting the plasmons. These plasmons excite this quantum dot cluster here, and this emission is again going to excite the plasmons, and this coupling is mediated by the plasmons between these two clusters which are far away. We measure the lifetimes as well. So one last example which I'll show you is the magneto-optical effects. So you can have Faraday or Kerr effect. Kerr in different geometries are possible. Faraday showed them in 1845, where the polarization rotation happens when you send linearly polarized light in a magneto-optical material. Right. So this happens because of the epsilon in the dielectric constant. We have these diagonal elements, and these off diagonal elements being non-zero will lead to these magneto-optical properties. Right. So it has large applications. We showed. I'll show you three different studies where the optical properties, magneto-optical properties of the material got changed because of this plasmon excitation, because of the strong local field, which is enhanced due to the plasmon excitation. So when light is incident, so you get this strong plasmon excitation of the local field, which leads to enhancement in your magneto-optical response. So here we showed 3 orders of magnitude enhancement in the Kerr signal just by patterning the top gold pattern. This is a grating structure in this case. And we also showed a novel longitudinal magnetoplasmonic intensity effect, where if you use this waveguide mode resonances, so if you take a little thicker layer, and you can use this plasmon mode, strong local field to couple to this waveguide mode, and then it passes out, and during this interaction, you can have change in the polarization of your incident light. So this is a you can have a plasmonic quasi-crystal. Instead of having a periodic grating-like structure, you can have this Fibonacci type structure where the width are modulated as per the Fibonacci sequence, and that leads to a broadband or multiple resonances at which this structure can respond compared to a single resonance which a plasmonic crystal shows. Okay. So this is again like most recent one which we are writing up currently is not just magnetic materials. Even if we take simple gratings, 2D grating structures which are made of metal discs, gold nano discs in this case, we see huge magneto optical response from these structures. This is because of the magnetic Lorentz force getting enhanced because of the resonant mechanism which we are showing. The plasmon resonance and the lattice mode, they match in this case. And when this happens, we can have Verde constant, which is as high as the highest Verde constant reported in the literature. So we have both for physics as well as for applications, we do these metamaterials. Right. So just to acknowledge, these are people who are part of this work. Ones in blue are the students and members in the lab currently at TAFR. The ones in blue here are theoreticians whom I collaborate with. As Professor R.P. Singh mentioned, at NPL, I'm working on SNSPD, and we have earlier designed the silicon photomultipliers at TAFR, which we are still looking to make second next gen devices there. And SNSPD designs are there. We made the initial devices and tested them. So we are improving on those studies currently. And at NPL, like I have one student working on single photon metrology, where we're looking at model dip and how the line shape is to be interpreted or understood. Thank you very much.
Thank you, sir. So we are waiting for our moderator, Dr. Satyan. Yeah, please.
Yeah. Thank you, Professor Achanta, for the wonderful talk on light metal interaction powered by various plasmonic nanostructures, basically metal nanostructures. So I'm sure there will be plenty of questions. So let me start with the ideas present in the auditorium. So I think the best way it will be that to come here and ask the question directly. So please raise your hand. So in the meantime, I will ask a couple of questions. So in the harmonic setup, when you have a single photon emission from the quantum dots, have you measured the indistinguishability of the photons?
Right. Yes. I mean, indistinguishability is basically the G2 is what we measure, and the dip shows whether we have one or two photons. So we did NVs, for example, nanodiamonds with different sizes. So where we took 10 nanometer, 20 nanometer, 40 and 100 nanometer dimension nano diamonds were studied, and we found that like 20 nanometer is the most ideal. If it is 10, like we don't see any emission, very difficult to see. If it is like 40 or above, like we see that we have more than one NV in it, and we see the G2 dip going not to 0 or less than 0.5, but it was always above 0.5.
Yeah, so G2 basically tells, right, the purity of the single photons, but the indistinguishability, like in this plasmonic setup, because of this lossy nature, right, it's very difficult. So you think that these single photon will be indistinguishable?
Right. Yes, you don't see, I mean, looking at the count rates, right? So these are of the order of like the highest we could get is of the order of like a few million photons per second. And these come at different times, right? And the polarization is basically controlled by the antenna, right? So that's where like these are absolutely indistinguishable, because the dipoles, we did the FTTD simulations to address this question. So what dipole orientation is contributing to it? So your polarization of the emitted photon depends on the orientation of the dipole in your emitter, right? So only the dipoles which are aligned in plane are excited, and that's how we know that like the polarization is also is well defined for these single photons which are emitted.
Okay, so I have another question. So in I think one of the slides you showed the cavity with lots of atoms, right, to achieve strong coupling.
Right.
So see, you have this strong coupling. So what is the interaction between the atoms?
It's a dipolar, like it's just the mu dot E term.
That the atoms are entangled, kind of.
Yeah, I mean they're not entangled, but then they're all coupled. They're an ensemble of things. So it's like they're too close together or bunched together, so that they don't. It's not just one single atom responding, but it's just the entire ensemble. It's called the cooperativity. They're all in a cooperative state, so that like they act as a bunch.
Just one quick in here. So the coupling strength goes as a square root of n, right? You say. In
Right.
this. Right? So why this square root here? From where it comes?
From where it comes, I need to check it up the model, like so, but right, where does this come from? No, I can't tell you right away, but it just comes from the model, like so.
Here is Satyen.
Yeah, so I think we can take.
Yeah, here Professor Vijay Sahu has raised the hand, so meanwhile you can give him a.
Yeah, Vijay, you can go ahead.
Yeah, thank you, Satyan. Yeah, Gopal, I have a couple of questions. First question is like this: how easy or difficult it is to prepare metastables? And second question is people, you're talking about trapping atoms. So do you think trapping atoms with metastables will have some advantage, or some kind of consequence? I don't know what kind of consequence one can have. And then Satyendra just now he asked about the kind of interactions. You said it is just dipole interactions, but van der Waals interactions also can play major roles here, right? So can you please answer to these questions possible?
Right. First thing is, if you take metal nanoparticles for right metal disks, as I showed, if we take them for atom trapping, so what we showed is that the trap minimum of the trap happens at about 20 nanometer for gold and about 12 nanometer for silver. Right. So one obvious question is that this plasmon mode for the metal nanoparticle metal layer interface, if the resonance is there, so then it's going to contribute to the decay of the atom which is so close by. Right. So what are the dynamics? Is it really the right structure? Needs to be checked. Right. And my supposition is possibly there will be effect because 20 nanometer is too close. But the other structure, metasurface, which I showed, that's much easier to make. And there we designed it for a distance of about 5 mm from the surface. Right. There we don't expect any effect of the surface on the dynamics of the atom. And second aspect is these are semiconductors, silicon pillars which have been used in the design. So there is no metal, so there is no plasmon mode existing there. It's just a dielectric surface which is patterned. Right? And your last question I didn't get.
Yeah, just I wanted to know like whether van der Waals interactions can also play important roles here, because
Absolutely. Right, they do. That's where I said that if they're too close, then yes, we need to take care of those things, and possibly they do affect the overall trap quality.
okay.
Right? Then that's a dissipative.
Yeah, if time permits, I have two more questions. Satyendra, do I have time?
You can go ahead.
Okay, so see, when you talk about this metamaterials, so what kind of theory one has to apply to study this band structure? Because like they are completely different than the ordinary matters, right? So one can still apply the same kind of theory or different. That is question number one. The last question is often when people talk about this metals for studying this materials, they consider gold. I don't know what's the particular reason. I know there are many metals. Why only people consider metals, whether it is very close to perfect conductor because of that reason, or it has some different, like some particular characteristic. Okay, that's all from my side. Yeah.
Right. Yeah. The first question, the band structure is calculated just using simple periodic boundary conditions. Right. you can I mean, we don't obviously use the electronic band structure calculations, but here you can use launch the electromagnetic radiation. You can do plane wave decomposition, right? Apply a plane wave coming at multiple frequencies or multiple wavelengths, and then see like how each one is getting. Basically, look at energy momentum conservation, which one is propagating, which one is non-propagating, and each of these modes, like so they come out nicely like a band structure. Right? The plane wave expansion method is one thing which is used, or just use a unit cell and do the electromagnetic field propagation studies with a periodic boundary condition. Okay? So that simply gives this, right? And the question about
Yeah, using gold.
right.
People are
So
using
why
gold.
gold?
Yeah.
So gold is good and bad. It's good because it's non-reactive, right? It doesn't oxidize. Unlike we can use silver or aluminum as well. The important point is the plasma frequency, which is I mean, we need to work in the visible to near infrared regions. Right. If you want to go in the UV region, silver or aluminum is better because the plasma frequency is little at shorter wavelengths. Right. So gold is used because it can work up to near infrared wavelength, and more importantly, it's because it's non-reactive and doesn't oxidize. We want to use silver or aluminum. We tried, and it's a mess because as soon as we take it out of the uh, our deposition system and patterning and all that, like then they're already oxidized, and then their properties matching them with the simulated ones will become little tricky, right? But one problem with metal is it doesn't stick well on any substrate properly. So what we do is we put a monolayer of MPTMS. Right? It's a polymer. Monolayer is possible. It has a NH bond on one side and a OH bond on the other side. So when we have a substrate, the OH bond sticks to the substrate and NH bond sticks to the gold which we deposit on top. Right? So this enhances the adhesion and it doesn't peel off easily. And
Okay,
it doesn't
thank
have
you very much for answering my question. Okay, thank you.
Okay, so there is one question in the auditorium.
Thank you, sir, for the talk. I have a question. What is the temperature of the systems that which you have studied, where the quantum dots are there coupled to the plasma mechanics? Because quantum dot excitons and phonon interactions play the key role in those kind of systems.
Right. So far we have used only room temperature for all these studies. The idea is to demonstrate these at the room temperature so that we don't use a cryostat or high pressure or something like that. Yes, there is a phonon broadening, but if you use a NV center, you always have the zero phonon line coming at around 530 nanometer, 580 nanometer, right? So we can use that as the zero phonon line emission is what we use. And in case of quantum dots, it's broad, but that's what we use. These are colloidal quantum dots which we use.
Okay. So, are there experiments done with quantum dots inside a photonic crystal cavities instead of that, like they couple to plasmonic cavities?
Right. So my initial work was all on photonic crystal cavities. The problem with them is that to go to strong coupling regime, weak coupling has no issue at all, right? But for strong coupling regime, as I mentioned, the G has to be comparable to kappa and gamma, right? So the lifetime of typically of an exciton is of the order of nanosecond. Right?
Yes.
So to get to that regime, we need the Q factor of the order of like 10,000. So the highest Q factor which we could get with photonic crystal cavity, we've tried different modes, but the highest we could get is about 7,000. And that's the best which people have seen in the planar structures, planar photonic crystal structures. So the cavity Qs were not beyond 7,000. So it was never in the strong coupling regime. So that was a challenge and still a challenge.
Thank
So
you.
that's where we moved to plasmonic and other resonances. Now we are using the bound state in continuum. I didn't show that, but bound state in continuum is mathematically zero line width or infinite Q factor. So we are working on them, embedding single quantum dots inside these BIC structures and looking at their emission or properties.
Thank you, sir.
So I think there is, okay. So one more question, if you can take, please come.
So, sir, I have a question. For different value of mu and epsilon, what is the value of refractive index? Is it positive or negative?
So it depends on, right, you have epsilon negative material, you have mu negative material. So if n is square root of epsilon mu, right, if one of epsilon or mu is negative, so then the square root of negative number, so n is complex number. So it's a lossy material, right? But if both n or n, both epsilon and mu are positive or both are negative, then n can be positive or n can be negative, right? So it depends on the values of the epsilon and mu.
Okay. So, if n is negative, and is it possible that n value is -1 or lesser than -1?
Yes, we can tune them, but for the perfect lens, to have lossless image, it is required that your n is equal to -1 with epsilon is equal to -1, mu is equal to -1. But
So,
getting
if n is
precise
-1,
value, right, precise value for a broad wavelength range is near impossible.
okay. So for n is -1, is it not contradicting that the speed of light is constant and it is maximum?
No, as I said, like, so in these media, the K and S are in opposite direction. So the energy is propagating in the same direction, so it doesn't matter. Right? It's not violating the causality. It's just the magnitude which is important, and the negative sign only tells us about the direction between K and S.
Okay. Thank you, sir.
I think there is one more question. So please come. So I think this will be the last one.
Achanta, I decided to ask a philosophical question rather than a scientific question. So the question that I have is, how can you be a pure researcher and an administrator and still do such cutting edge science? Because I've followed your works over the last 15, 20 years, and you really seem to catch the trends of frontiers of photonics and have continued to contribute so strongly from India. I think you are probably one of the finest photonic scientists that I know globally, and definitely one of the top from India. So can you share the secret of your success, Achanta, with the young researchers and also the students? Thank you.
It's very kind of you, Ranjan. So yes, I wish I know there is any thumb rule or something. So it's like collaborators like you which make life so much more exciting and introducing to newer problems and newer challenging works. So I would like to thank all my collaborators once again for pushing me, right, and pinging me whenever there is some delay from my side, like, okay, so to put me on track. So I think the credit goes to all my collaborators, including you. Thank you.
So thank you, Professor Venu Gopal. So for accepting our invitation to deliver 84th PRL Amrut Vyakhyaan. and also interacting with our audiences. Final stage of this Vyakhyaan, I would like to invite my colleague Dr. Manas for the vote of thanks.
Am I audible?
Yes.
Yeah. Thanks, Professor Sahu. Friends, it is an honor for me to propose a vote of thanks on today's session. First of all, on behalf of PRL, I would like to thank today's speaker, Professor Venu Gopal, for sharing his knowledge with us on metamaterials, how to engineer them, and their wide applications. It was truly a wonderful Vyakhyaan, and I must say that is, as you said, it's a nice tutorial, and I'm sure most of our scope participants must have enjoyed this tutorial and learned a lot. Sir, once again, we thank you for your time and also patiently answering all the questions raised by our colleagues and participants during the question and answer session. Thank you, sir. Next, I would like to thank Professor Anil Bharadwaj, Director PRL, Professor Pallam Raju, Dean PRL, and all the Vyakhyaan committee members for their continuous efforts, making this Vyakhyaan series keep going. Finally, our special thanks to all the participants and our viewers who have joined us through various platforms. Thank you all for your time. With this, we come to the very end of today's chapter of PRL's Vyakhyaan. See you again next month with another 8 interesting Vyakhyaan. Have a great evening. Thanks.
Thank you.
Thank you, sir.
Thank you.
Thank you, Professor Venugopal.